Okay, let's unpack this. Have you ever genuinely stopped to marvel at your bones?
Hmm.
I mean, these aren't just rigid sticks holding us up, are they? They're dynamic, living structures,
Absolutely. Living tissue.
silently performing this incredibly complex dance of forces every single day. They keep us upright, let us move, basically hold us together.
Yeah.
But how do they actually do it? How does something that feels so solid also manage to be, well, flexible enough to absorb impact?
Right?
And what exactly happens when those forces push past the bone's limits? That's the fascinating mystery we're diving into today.
It truly is a marvel. And what's so compelling here, I think, is that the very principles of engineering are at play, right inside our own body.
Engineering, huh?
Yeah, determining not just if a bone breaks, but precisely how and why. We're talking about biomechanics, basically the study of mechanical laws relating to how living things move and are structured.
Okay.
Specifically, we'll explore how the composition of bone material and its structural arrangement are just exquisitely designed to resist various mechanical loads.
Loads like bending and twisting.
Exactly. Our deep dive will demystify concepts like bending and torsion, connecting them directly to common bone injuries you might see,
Mm-hmm.
you know, from the unique challenges of children's growth plates all the way to adult stress fractures.
Yeah, those sound familiar. Okay, so we've got a stack of fascinating sources here, articles, research papers, some notes. Our mission is to pull out the key insights
Mm-hmm.
so you can quickly grasp the mechanics behind bone strength and, unfortunately, bone failure, too. You'll walk away with a whole new appreciation for your skeleton, hopefully.
I think so.
So let's start with the absolute fundamentals. What exactly determines if a bone will break?
Right.
Our sources, they say a fracture isn't just a crack, it's a disruption in the continuous structure of the bone.
That's the definition, yeah.
It sounds simple, but it seems to boil down to a core idea. A fracture happens when the load applied is greater than the bone strength.
Load exceeds strength. Simple equation.
But that bone strength, it's not just one number, is it? It's dynamic. It depends on several things.
Exactly. It's a function of factors. Primarily the bone's overall size, its specific shape, which is really important, and its density, how much mineral is packed in there.
Okay, size, shape, density. Got it.
And, well, the story gets even more complex when we look at the nature of the fracture itself. What kind of break is it?
Right.
That's influenced by a whole host of variables. We're talking about the specific direction of the force.
Like straight on versus sideways.
Precisely. And its sheer magnitude, obviously.
Mm-hmm.
But critically, the rate at which that load is applied.
Speed.
Yes, speed matters.
Yeah.
A rapid, sudden impact is far more damaging than a slow, steady pressure. Think falling versus leaning.
Okay, that makes sense.
Then there's how long the load is sustained, and maybe most importantly, the overall health of the bone itself.
Health of the bone.
Its material composition, the ratio of flexible collagen to hard minerals, and its intricate structural arrangement, like we mentioned. Think about normal bone growth, how it matures, from the cellular level right up to the tissue you see. This process constantly impacts how well bone handles loads. Even things like, loading from exercise versus unloading from bed rest. That affects mineralization.
So use it or lose it, basically.
To an extent, yes.
Yeah.
It directly influences its ability to resist these stresses,
That's a great point about bone health. We should definitely circle back to that when we talk injuries.
for sure.
But now, here's where I think it gets really interesting. Let's dig into the first major type of mechanical load.
Oh,
Bending.
okay. Flexure.
Yeah, flexure stress. Imagine your femur, that big thigh bone, right? The forces it feels when you run, jump, even just stand, a lot of that is bending.
Mm-hmm. A classic example.
Our sources define bending, or flexure stress, as simply the stresses caused by that bending action. They
Oh.
use this analogy, the three-point bending of a beam.
Ah, yes, the standard engineering test.
Right. Picture a plank on two supports, and you push down in the middle. It bends.
Exactly. You've got the downward force you apply and the two upward reaction forces from the supports holding it up.
And engineers use these hypothetical cuts inside the beam, or the bone, to see what's happening internally.
That's the method,
Mhm.
to analyze the internal forces. And what you find is that bending generates both normal stresses,
Normal meaning.
meaning tension, a pulling force, and compression, a pushing force. It also generates shear stresses, which act parallel to the cut surface.
Okay, so if you bend a bone, one side gets stretched out tension and the other side gets squashed compression.
Precisely.
But is there like a zone in the middle where not much is happening?
That's a crucial insight.
Yeah.
You've just described the stress-free layer or the neutral plane.
Neutral plane, okay.
It's this invisible but incredibly important dividing line within the bone's cross-section. Along this plane, there's surprisingly little longitudinal stress, not much stretching or squashing right there.
Oh.
So if you picture that bending bone again, one side experiences maximum elongation tension. The opposite side sees maximum contraction compression.
And that neutral plane tells us where the bone needs to be strongest?
It helps explain it, yeah. It
Yeah.
shows where the stresses are most intense,
Yeah.
usually furthest away from that plane. So material there contributes most to resisting the bending.
That makes so much sense. Okay, so the actual stress, the flexural stress, depends on a few things then. Our sources mention the bending moment, how much it's being bent,
Right. The magnitude of the bending effect,
the distance from that neutral plane,
how far out from the center you are.
and this property called the area moment of inertia, I.
Yes. Incredibly important. It's not just some abstract math concept. It's a fundamental structural property. It literally describes how resistant a cross-section shape is to bending.
Okay, resistance to bending.
Think of a simple rectangle, like a 2x4 piece of lumber. Its I value is 112 bhra. B is the base, h is the height.
Wait, h cubed?
Cubed, that's the fascinating part. Resistance to bending scales with the cube of the height in the direction of bending.
Wow.
So a tiny increase in a bone's diameter, especially in the direction it's likely to bend, gives it a massive boost in bending strength.
Which is why our long bones aren't pencil thin, they have thickness.
Exactly. It's nature's material science at its best.
Right.
It allows bones to be relatively light but incredibly strong against bending. Very efficient design.
So geometry is key, way more than you'd first think. And our bones aren't simple rectangles, obviously. They're complex, irregular shapes.
Absolutely. And that's where calculating I gets a bit more involved, but the principles are the same. For complex, real-world bone shapes, you need ways to figure out the total I.
How does that work?
Well, if a cross-section is made of simple shapes whose centers happen to line up, you can sometimes just add their individual I values, but that's rare in biology.
Right, bones are lumpy.
Usually the centers of different parts of the cross-section aren't coincident,
Mhm.
so we use the parallel axis theorem.
Okay, sounds important.
It is. The formula is I parallel axis equals I parallel axis plus A toric. A toric is the moment of inertia of the shape about its own central axis, A is its area, and D is the distance between that axis and the main axis you're bending around.
So it accounts for how the material is distributed away from the center.
Precisely. It highlights how complex bone shapes, maybe thicker on one side or hollow, efficiently distribute mass to maximize bending resistance where needed. It's how engineers and evolution optimize structures.
Okay, that's bending covered. Really clever stuff. But our bodies twist too, right? Like pivoting in sports or even just opening a stubborn jar. What about torsion?
Perfect segue. Torsion is the twisting of an object because of an applied torque, a rotational force.
Instead of pushing or pulling, it's twisting.
Exactly. And this torque creates a specific pattern of shearing stress across the bone's cross-section. Think about wringing out a wet towel.
Yeah, you feel the twist through the whole thing.
That's torsion generating shear stress.
And what's happening inside the bone when it twists? Where's the stress highest?
Good question. With torsion, the shear stress is actually greatest at the outer surface of the bone and decreases linearly towards the center. Right at the very center, there's theoretically zero torsional shear stress.
Opposite of bending, where it's high on the outside surfaces.
In a way, yes. Though bending has both tension and compression, highest on opposite outer surfaces. Torsion is purely shear stress, highest all around the outer circumference.
Okay. And what determines how much shear stress there is?
It depends on the applied torque,
Uh,
the radius r from the center to the point you're interested in, and another crucial property, the polar moment of inertia, usually written as J.
so J is for twisting, like I is for bending.
Exactly. J measures a cross-section's resistance to twisting forces. For a solid cylinder, J is to the p rho, where rho is the outer radius.
Again, with the radius to the fourth power, small changes have big effects.
Huge effects. But many of our long bones aren't solid, are they? They're hollow tubes.
Right, like marrow inside. Does that make them weaker?
Counterintuitively, no.
No.
It actually makes them more efficient at resisting torsion and bending for a given amount of material. For a hollow cylinder, J is the inner radius.
Wait, being hollow makes it stronger for twisting.
Not stronger overall than a solid bar of the same outer diameter, but much, much stronger for the same amount of bone material or weight.
Ah, the efficiency argument.
Precisely. It's brilliant bioengineering. If you connect this to the bigger picture, you see these structures are adapted for multiple load types. A hollow tube puts the material further from the center, where torsional stresses are highest, and also further from the neutral axis for bending.
Maximizing both I and J for the least weight.
You got it. Maximum strength, minimum weight.
Hmm.
Crucial for moving efficiently. It's the same reason bicycle frames or aircraft parts are often hollow tubes.
That's a fantastic aha moment. It's not about being solid, it's smart material distribution.
Exactly. And there's another neat connection. The polar moment of inertia, J, can also be found using the perpendicular axis theorem. J equals Ix plus Iy.
Relating J back to I?
Yes. It says J about an axis perpendicular to the cross-section equals the sum of the area moments of inertia about two perpendicular axes lying in the cross-section plane. It shows how resistance to bending in different directions relates to resistance to twisting. It's all interconnected.
Wow. Bones are truly integrated systems. Okay, so we've covered the mechanics of bending and twisting, why bone shape matters so much, but what does all this mean for your bones, in the real world?
Right. Theory to practice.
We said fractures happen when load bone strength. Let's
Yep.
look at some specific injuries.
Okay. We can see this play out clearly. Take children's bones, for example.
Yeah. What's different about them?
They have relatively more collagen compared to adult bones. Collagen is the flexible protein component.
So they're bendier.
Exactly. More pliable, like a fresh green tree branch compared to a dry, brittle one. It'll bend and maybe splinter before snapping cleanly.
Ah, so that's why you hear about green stick fractures.
Precisely. Green stick fractures and incomplete fissures are common. The bone partially breaks or bends. It doesn't completely sever. It gives them a bit more resilience for, everyday tumbles.
That makes sense. Material composition, changing the failure mode. What about the other end, like osteoporosis? That affects density, right? How does that fit the load strength idea?
Great question. Osteoporosis dramatically lowers bone density, making bones porous, brittle. Think of healthy bone like dense wood. Osteoporotic bone is like that wood riddled with tiny holes.
So less material there.
Less material, yes, but critically, it reduces the effective cross-sectional properties. The I and J values plummet.
Ah, so it weakens resistance to bending and twisting.
Significantly. A minor bump or fall that healthy bone would shrug off can cause a major fracture. It shows how bone health drastically shifts that strength threshold down.
That's really impactful. Okay, what about stress fractures? You hear about those in athletes a lot. It's not usually one big hit, is it?
No, exactly. Stress fractures or fatigue fractures are a perfect example of how repeated lower-level forces cause failure over time.
Like running.
Running is a classic cause. Think of the repetitive impact.
Mm-hmm.
What happens is this increased frequency or magnitude of loading causes a stress reaction. Tiny microdamage occurs. Invisible cracks.
Okay.
Then the body's repair crew, osteoclasts resorbing damaged tissue, osteoblasts laying down new bone, tries to fix it.
But
But with a stress fracture, the key is that the repair cycle gets interrupted. New microdamage happens before the previous damage is fully repaired.
so damage outpaces repair.
Exactly. It's a vicious cycle. Eventually, enough damage accumulates to become a visible fracture. Usually starts in the outer cortical bone layers, where stresses are often highest.
And can become a full break if you ignore it.
Absolutely. If the loading continues without enough rest for repair, it can progress to a complete debilitating fracture.
Wow. That's incredibly relevant for anyone doing repetitive activities. A powerful reminder about rest and recovery.
Mm.
Now, what about those epiphyseal injuries? You mentioned them earlier, especially for younger people.
Yes, epiphyseal injuries to the growth plates, they're really significant. About 10% of acute skeletal injuries in kids and adolescents.
Growth plates. Those are the soft bits at the end of bones where they grow from.
Essentially, yes.
Mm.
They're cartilaginous plates. Injuries can happen to the plate itself, the joint cartilage nearby, or the apophysis, those bumps where tendons attach.
And why are these so critical?
Because the epiphyses are the growth engines of the bone. Damage here either from a sudden acute injury like a fall or from repetitive overuse like in youth sports
Yeah.
can injure these delicate plates. And here's the crucial point, a real aha moment for parents or coaches. That injury can potentially cause the growth plate to close prematurely,
Close early, meaning...
meaning it stops growing. It fuses.
Yeah.
This can terminate bone growth in that specific area.
Wow. So an injury in childhood could literally stop a limb from growing properly,
No.
lead to length discrepancies or deformity?
It can, potentially.
Yeah.
Yes. That's a truly profound implication.
Yeah.
It makes understanding these biomechanics vital for prevention, for careful training loads in kids, for proper treatment.
Definitely. It really brings home that question. how much load is too much, and how that varies by age, health, activity. It really underscores why knowing this stuff matters.
Absolutely.
We have covered a tremendous amount of ground today. Wow.
We really have.
We started with just appreciating bone strength, then dug into the mechanics, bending, twisting, IJ.
The engineering principles.
Yeah, and then saw how it plays out in real injuries. Green stick fracture, stress fractures, those critical growth plate issues. We've taken some, frankly, complex biomechanical ideas and hopefully made them clearer, more actionable for you.
And that's really the goal, isn't it? Knowledge is most valuable when you understand it and can apply it. Reinforcing these mechanical principles is vital, not just theory, but practical stuff.
Like injury prevention.
Injury prevention, designing better protective gear, even just understanding rehab after a fracture. So next time you're moving, maybe think about it.
How the forces work.
Yeah, consider how these forces impact your everyday movements,
Right.
whether you're, lifting groceries, taking a walk, or really pushing your limits training for something.
Absolutely. So next time you take a step, lift something heavy, or even just watch a child run around playing, maybe take a moment.
Okay.
Appreciate that incredible, intricate engineering marvel that is your skeletal system.
Mhm.
It's silently doing all these complex calculations, managing forces to keep you moving, enduring, thriving. How might understanding these mechanics change the way you approach your own physical activities, or even just how you observe the amazing world around you?